Authors, please take the seats. First presentation will be on the topic design and integration of cast blasting with dragline operation to enhance operational efficiency by the IIT ISM Dhanbad. Author is requested to kindly come and join us, please.
सेकेंड सेशन हम लोग तुरंत स्टार्ट कर रहे हैं. वी हैव विद अस SS राय सर फ्रॉम IIT ISM धनबाद. We have with us Ritesh Tiwari from Sasan Coalfields Limited. I request Naveen Rai sir from Northern Coalfields Limited to please take the seat on the dais. The chairman of this session is Shri Satish Jha sir, Area General Manager Dudichua. And Shri Indrajit Singh sir from Area General Manager Kakri. I request you sir to please take the seat on the dais.
This session will have 5 presentations including one virtual presentation. I would like to request our chairman sir, Sri Satish Jha sir, kindly come on dais. Thank you very much, sir. Now we will start the session 2 of the day 1. Over to you, sir.
Very good afternoon. In this second session, after lunch, most of the audiences are sleepy. I hope this session will wake them up. Drilling and blasting. Rai sir, we expect that, and a little bit of advice to our authors, that we come to this subject and your recommendations so that the audience benefits from that. Introduction and brief background can be neglected or briefly dealt with. So, in anticipation of a waking up session, I invite Dr. S.S. Rai sir to please begin.
Thank you, Chairman sir, and Co-Chairman sir, and good afternoon to everyone. I know this is a difficult time post-lunch. People start feeling sleepy. Let me try if I am able to wake you up. So I'm going to talk about the blasting and cast blasting in particular, which is an integral part of the dragline. Because globally, wherever you have the dragline operations, you have a cast blasting as an integral part. So, can you move the? Okay. So basically, the idea is to, again, anything, whether it is innovation or anything that we try to do, the purpose is to increase the productivity or the operational efficiency. The first slide is, these are the four broad parameters which will help improve the operational efficiency of the mining system. So beginning with the mining plan, your operation will be efficient if the mine plan is efficient. That's the basic concept. And the equipment system. Which equipment system you select? Like dragline equipment system is inherently more productive than the shovel dumper system because it completely eliminates dumpers. So selection of equipment also plays a very important role. Then the operator skill. So that most of us are aware. And then the operating conditions like the haul load, phase conditions. So these are the four broad factors that affect the operational efficiency of the mining equipment. Probably the blasting comes under the mining plan. So we'll discuss more on the blasting. Next slide, please. So, brief introduction of the dragline mining system. Dragline mining system is also known as the high bench mining because dragline operates on the high thickness like 30 meters and above. So, it's known as the high bench mining. And there are certain advantages because you eliminate number of benches, your slope becomes steeper, and if your slope becomes steeper, that running slope will lead you to lesser running stripping ratio. Because it's coming like this slope and this slope. If you are moving this slope, you are moving more over to get same ton of coal. So, okay. And as I said, it is one of the most efficient mining system. Main reason is that it completely eliminates trucks. The fleet size is smaller. Production cost, CMD sir was saying, is one of the cheapest way of moving the material. Bigger capacity, minimum size is 24 cubic meter, which is also the smallest size in dragline. And the high reliability, very robust machine. If the machine is okay, it hardly goes breakdown, it just go on running. Therefore, the draglines have emerged as a dominant overburden stripping system across the globe. Next. So, as I said, the cast blasting is an integral to dragline operations. And it's not a normal cast blasting that you maximize the cast. It is a cast that we want to achieve to have a maximum overall system productivity, which include dragline excavation, which include a dozer push, and also the cast blast profile. So profile becomes very important in this. Profile plays two important role because it also fixes the dragline setting position. And that you fix considering the two limitations of dragline with the digging depth and the dumping radius. So it's not that if your blast drop is maximum or the cast percent is maximum, you are achieving the maximum product. It's not the case. And for every dragline it varies. So we have to design a cast blast in such a manner that it gives me the maximum productivity for the system as a whole. not cast blasting is standalone or the dragline standalone. So that's the whole philosophy that I'm going to explain, and this picture explains, like if you look at the solid mass, after the blast it has taken the blast profile, and the dotted line, that's the material is to be dosed, because that's the level where dragline is going to sit and excavate the material and expose the coal. So this is the whole philosophy. So if the blast drop is, as I said in the beginning, is more, then you screw with the dragline sitting level. And then dragline will work more, either dragline or you have to bring extra material to make a sitting pad for the dragline. So that's how the cast blasting role in dragline operation becomes very critical. Next slide, please. Next, please. So this is a case study that we did along with the Reliance team, and I'm very thankful to my co-author, who is Umesh Kumar Mato. He was the project director there, and also two MTech students who were doing projects in IIT ISM, Sukesh and Sai Ram Teja. Both are now working in Mahanadi Coalfield, and they were part of this whole exercise. So just to explain, to begin with, this is the geo-mining condition of the Reliance coal. In the top you can see the dragline is that interburden between Turra and the Pureva. That dragline was deployed, and the thickness there, the cover was of 60 meter, and the dragline size was 6120. So that's where, and the decision that Reliance was operating, that they were blasting 50 meter bench at a time, and the 10 meter they were pre-stripping by the shovel dumper. So that's, and their mining method was extended bench methods. So the left hand side, this is the photo there, and on the middle it just explains the digging sequence, the different position dragline takes while taking the key cut as well as the box cut to expose the clone. And the last one is just the diagrammatical representation of the dragline system, dragline mining methods, which material is takes from where and extend the bench, and then how it uncover the coal. So since the topic is different, so I'm not going to dwell much on the dragline mining method per se, but we'll discuss more on the cast blasting. So initially we went through a number of blasts. Almost like around 20-30 blasts we studied, and these were the summary of the parameters. If we look at the type of explosive or the doped emulsion with 75 to 80% emulsion and 20 to 25% NFO, and all these explosives were manufactured by they themselves in their plants. The specific gravity was 1.1 to 1.3. Then the velocity was 4800. So these are all specific charge was varying from across the blast, 20-30 blast, 0.66 to 0.69. Burden was by and large fixed, uniform, 10 meter. Spacing to burden ratio was varying between 1.2 to 1.25 to 1.35. Angle of drills, all were the vertical drill holes. But these are some of the parameters which affect the performance of cast blast. So I'm just trying to enumerate. Top stemming, norm is 0.7 to 0.8 of the burden, and that's what they were filling. Decking, 2 meter at the bottom. So these are all sort of a data that we collected. Bench height 46 to 51, bench width 55 to 80, because like in case of Amlori, yesterday I was seeing the geological map of Amlori. It is quite singing strike length. So same is also there, it quite swings. So where it swings very steep, then you tend to have your bench width less, just to manage that swing direction, strike directions. Height to width ratio was 0.7 to 0.85. Length to width ratio, this also very important for achieving a good cast. Percentage 3 to 4. Drill hole pattern was staggered. So these are some of the data we collected, and I'm just presenting the range of all close to 30 blasts. And the performance of the blast was on the right hand on the top. So from the bench height ranging from 46 to 50 and pit width 57 to 78, the cast percentage was varying a lot. The material was same, it was varying from 22 to 40%. Rehandle on an average was 30%. Average bench height reduction, that also varied quite a lot, because that's the reason probably why the cast percentage also varied. So the blast drop after the post blast, the reduction in the bench height was also varying from 13 to 22. And since we had the data, so we worked out this empirical relationship, though I don't believe really in empirical relationship, because you see, we express the whole relation with the help of a straight line or maybe a curve, but a number of points were both sides of the curve. So it's never accurate. but in absence of really having an actual mathematical equation between the variables known. So we believe in this. So this is what we drew. Then we also collected the data of the total for the entire year. 18-19 was the year. So total blasted volume almost like 9.8 trillion. So these are all the data. You can see there are different, like the dodging hours. Dodging which was deployed for the dragline was 590 hours it dodged. Operational delays on account of many things, like draglines may be waiting for the blasting to happen, or some cable shifting was going on, or maybe dodging work was going on, because that there was operational delays. So breakdown and maintenance was almost 1930 hours. Available hour was 6830. Utilized hour was 5986, almost close to 6000 hours. Digging hours, including the high wall, so same 5689, because this was a pure digging hour. Machine was actually digging, not marching, etc. Work and certain time before and after. So all this thing we calculated, and then we measure the productivity from these data. And we split the productivity into 3 components. One component was when the machine is digging, what is the productivity? And naturally that will be the highest productivity. Second productivity was the productivity of the machine was being utilized, means the HMR reading was being clocked. So in that scenario, machine may be digging, machine may be marching. So when machine is marching, it's an unproductive work. So that includes the productivity of the utilized hour, and then finally productivity of the systems, dragline system productivity. This is the total production that dragline made divided by total available hours. So, and this is where the whole game plan was. Our objective was to maximize the dragline system productivity as a whole, which included the dozer push, rehandling, etc. So we were not looking at any other productivity, because digging productivity you can manage. If you reduce the swing angle, you can increase. But over the year, what is the maximum productivity, which includes all the parameters? And that's what is the real scenario. So this is where we were interested. And move to the next. Again, the same analysis was there. The variation in cast percentage and resultant blast drop caused variation in the productivity of dragline system when the cast percentage were very high, more than 40%. And the blast drop was in the range of 18 to 22 meter. Associated cast profile did not support an efficient operation. So when the blast drop was too much, means the cast percentage was very high for this particular dragline, the productivity was going down because dragline was idle for many hours on account of dozing, or dragline itself was doing unproductive work, making pad for itself. So which is an unproductive work. So that drawing just explains about the blast drop and different, like the dragline setting level, all those stuffs. So, okay. So then what we did, we used a software called the DragSim to model the entire dragline operation, where we could also model the blast profile. And we modeled first we started with, we took a blast profile from the actual scenario, we modeled that in the softwares. And this is the sum that use of software, while modeling we take all the parameters. We take the geological conditions, machine parameters, production parameters like the cycle time, etc. So everything we model, including the profile. So can we move to the next? And then once we modeled, then we compared. We had the actual scenario and we had the modeled scenario. So actual figure, say for example, cast percent of that particular blast that we were modeling and the dragline operation was 27.2%. Result in the simulated model came around 25.9. So there was a variation of almost close to 5%. Likewise, rehandling, there was 22% in that particular operation. Our model said that's 22.8. Productivity 1650. Our model said 1628, which is very close. And we actually really modeled all those digging sequence and the dragline mining methods. Average swing angle also we measured. This is a little misleading because there is nothing called the average swing angle in dragline, because every digging position is sets, and in this particular it has 6 digging positions. So every digging position has a different swing angle. So, but average was coming close, so the variation was well within limit. Normally we consider if it is within 5%, we will treat that the model is okay to go ahead. So this model was calibrated, and then we run the scenario. We change the blast profile and looked at what productivity we are getting. And we did a number of scenarios. I am presenting 5 scenarios where, if you look at this, the bench height, these are the 5 options. Pit width we varied, cast percentage we got different from the model. Rehandle was this, dodging volume was this, average bench height reduction in the different models. These are not the real blast, these are the model blast based on one of the dragline operation that we modeled and calibrated in one of the scenario. Dragline excavation productivity, you can see it's digging productivity. Here by mistake, please don't get confused. This is the digging productivity. So that is one. Then the system productivity, and then the I think there's something garbad here. But anyway, let's for the dragline system productivity. See, you can just notice in option 3, while we got the maximum system productivity of 16.8.2, but not necessarily the digging productivity was the highest. While the digging productivity was not the highest, but the system productivity, which included the operational delays, dodging hours, etc., during which the dragline was not able to operate, not able to dig. So option 3, we found that in these options and that particular profile, the dragline system will give the maximum productivity. Again, to reiterate, is the dragline excavations plus dozer plus the cast percentage. Next. So this is the option 3. And the outcome was that the optimum cast percentage we could achieve was the 35.9, over which our productivity was going down, below which also productivity was going down. And the blast drop was 17.6 meter. This, of course, is a model, is not a real scenario, and mining is not a 100% business. Whatever you model, there will always will be a gap. We learn from the gap, bring it back to the model, and then again try to refine it, and that's how the whole process goes on, but we never achieve 100%. So that's what the experiences says. Mining is so much of variation, we can never achieve 100%. Every time we are trying to achieve 100%, but still there is a gap between what we have planned and what we actually achieved. Next. Then, with the help of the project SESSION team, we executed that blast to achieve that blast profile. And this is the blast profile we got. This is all from the laser scanner, and then we converted that laser scanner into the AutoCAD drawing, and we tried to have that, and we got for the same day, 15.70 was the blast drop, and cast percentage was a 33.20, and the bench height reduction was 15.70. As I said, we could not achieve what we wanted, but still there was an increment. There was some incremental benefit. That's what we achieved. Therefore, next slide. And this also we measured. The blast design, we use the JK Sim blast to model the entire blast, and this firing sequence, and also the powder factor, the number of boreholes. So we all tested this for the 177 milliseconds. This is the firing pattern for every 177 milliseconds, and then the top one is the firing pattern, and there is a powder factor. The constant decrease in the powder factor, and the volume was continuously increasing. So this was the finding there. So therefore, in the nutshell, we have developed a methodology, still to prove. But we developed for the cast blasting. This is not for the fragmentation blast, which in most of the places India it is practiced. It's a typical cast blasting for dragline operations. So what is the design objective? We need a pit geometry. What is the bench height and the bench width? Because cast blasting depends on the H by W ratio, L by W ratio. If height is more, gravity will support you to have the more cast, whether it is beneficial or not. So pit geometry we have to design, cast percentage we have to design, cast profile we have to design, and finally dragline system productivity. The goal was to optimize everything. Then we undertook that into a simulation. So we simulated doing that. We have to simulate that and have the desired cast percent, the cast profile. Then we design the blast, for which we have 2 parameters. One is on the left hand is an uncontrolled parameter, which is site specific, rock characteristics, geology, dragline operating plan, mining method, etc., which is given. Then on the right, we have the design parameters. We can select explosive, various design parameters like burden, spacing, initiation sequence, blast hole diameter, burden stripping. So all those where you should design, and then you test it. You run a trial blast. If you achieve the objective of maximum productivity, you go ahead, produce the report. If not, you go and change the design parameters, try to achieve that. So this is a reiterative process which has to go on until we get the desired results. So thank you very much. This is all I had to say.
Thank you, sir. Quickly we move to the second paper of the session. From NCL, it is Positivistic Approach in Drilling and Blasting by Shri L.P. Godse and Shri A.K. Pandey.
Thank you, sir. Good afternoon. Respected DTO, sir, DTP NP, sir, our chief guest, and all dignitaries present here. Myself, Ajay Kumar Pandey, Manager Mining, Production Department, NCL Headquarters. My paper was on a positivistic approach in drilling and blasting and HOE patches of NCL project. Come to the first slide. First slide. Okay. This positivistic approach is in drilling and blasting is basically directed by our Honorable CMD, sir. And this approach is being well executed in the guidance of our GM production, Sri L.P. Godse, sir. Under this topic, what I will discuss, what blast design were being used in previously in HOE patches, and what modification we have done in blast design, and what result we are getting after this changing in blast design. First, we will discuss the prevailing practices as HOE patches. As since 2006, we are dealing with HOE, and we have 6-meter drilling, and our dia of drill in HOE patches is 159, and nearly 80% of removal is being done by HOE contractors. Powder factor range from 1.5 to 1.9. This is all about prevailing practices. Next slide. This is all about trends in last year. You can see the contribution of HOE percentage is day by day increasing. In 2019-20 is 73%, 2021 is 77, and in 21-22 is 79, and in 22-23 it will be expected more than 80%. And in the same way, explosive consumption in HOE is also increasing. It is first 64, 68, then 70%. You will see the explosive cost per ton is 143 rupees per ton, and cost of coal per ton is 986.12. So you can see how much explosive is important to us. It is nearly 14 to 15% of the total cost of coal per ton, explosive cost. So it is very important to check and curtail where we are using explosive, and in the way blast design or in the other way. So next slide. This is the cost per ton distribution of our all expenses. You can see 31% on HOE and 19% on salary and wages, and come to the third part is 50% explosive. So explosive is a major role in expenditure. And this is project-wise cost per ton distribution. Here you can see Dudichua, Lori, Nigahi is on the highest side. It is just also because of the highest stripping ratio. And this is the graphical representation of what we had seen in the last slide. You can see Amlori, Nigahi, and Bina is also on the highest because of the highest stripping ratio. And explosive cost versus total cost is also high in that mines. Next slide. This is the new blast design parameter where what we are discussing. Burden is actually the distance of the free phase from the first line hole and the second line hole. Spacing is the hole to hole distance. And subgrade drilling Stemming height is basically to contain the gaseous energy, and D is the hole diameter, the sectional and plan view of the all blast design parameter. Come to the next slide. This is the 3D representation of the blasting patch, where you can see spacing, burden, stemming, charge length, subgrade drill, and free phase. This is all. Next slide. Come to the blast design. How we can calculate all the blast design parameter. First, we have to fix what is the basic thing. First, we have to fix our hole diameter. In HOE patches, we have only 159 mm diameter drill machine. So we will first fix this hole diameter for other calculation. Now you can see on the right side, there is a burden calculation. B is equal to 8 into 10 power 3 into D, the cube root of STV by SGR. STV is the relative bulk strength of the SME. This is 130, and 4 is the basic 100. And SGR for NCL is 2.35 specific gravity of rock. So burden is coming 4.66 meter. Come to the next slide. This is blast hole depth. It is very important. Rule of 60. It is very important and famous rule where D is the 159 for HOE calculation, and what we are getting LH is 9.5 meter. Here you can see what we are doing in the past is 6 meter drilling. It is against the rule of 60 actually. So as we are against the rule of 60, and coming to the right side, you can see stiffness ratio L by B ratio. If we calculate L by B ratio is also, we will be calculating next slide, stiffening ratio analysis. Here you can see, go back to the slide. Here you can see if L by B ratio will be 1, 2, the result will be poor to fair, and if L by B ratio increases, the result will be going from poor to excellent. Where it is L by B ratio directly proportional to length of hole, here we are, that's why we are thrusting on to increase the length of hole from 6 meter to 9.5 or 9 meter. Come to the next slide. This is the L by B ratio analysis. Prevailing practices, we have a stiffness ratio of 6 by 4, 1.5. It is from very poor to fairer range. And next. In current practices, we have a stiffness ratio near about 2. That means it will be, the result will be better according to stiffness ratio. Next slide. This is the calculation of stemming height. First thing is, it is the minimum stemming height. You can optimize this. Stemming height is 0.7 into burden. The stemming height will be coming 3.5 meter. You can increase it depending upon your rock strata condition, depending upon your explosive strengths. Here is spacing. Spacing is S equal to length of hole plus 2 into burden divided by 3. This will be coming 6.3 meter. And this is the whole scenario in a single slide. Drill dia is fixed 159, burden back. Drill dia is burden is 5 meter, blast hole depth is 9 meters, spacing 6.5, stemming height 3.5, and you can see charge per hole 137 and 5.5 meter charging length. This all parameters based on the uniform geological condition. You can vary it depending upon your strata condition. Next slide. This is scenario after implementation of 9 meter drilling. What you are getting that fragmentation increased, fly rock control, ground vibration and air velocity effect also improved. And most important thing, economy. Powder factor increase up to 28% in 9 meter drilling versus 6 meter drilling. Next. Analysis patches of the HOE. Currently, we are, from this guidance, we have deployed 31 drill machines, and currently we are going up to 32% drilling in 9 meter. And in next slide, we will be discussing what is the benefit of this. This is the blasting analysis, advantage of new practices of 9 meter. First, reduction in number of holes per meterage, reduction in number of blasting rounds, because there is patch of 9 meter, reduction in machine marching time, intern idle time, better control in fry rock. You can improve fragmentation of blasted material. Safety parameter also improves. And in same way, less interruption in departmental hour working and less damage to OH line. Now this is saving. What we have saved in 9-meter drilling. If you will go for 9-meter drilling, you can see the detonating fuse DF we will be saving up to 3,250 kilometer of DF because of 9-meter drilling in the month from November 22 to March 23. And in cord relay, you can see the saving of 148 kilo numbers. In CED, electric detonator, you can save 4.1 kilo numbers, and that's where the main point is meterage. Meterage is totally saving of HOE contractors. It is saving of 1534 kilometer of meterage. And if we will calculate the cost by 85 rupees per meter, it will be 13.04 crore rupees of HOE. Another advantage by HOE is you can see the productivity is increasing from October. Total NCL productivity of HOE patches is increasing 3873 cubic meter per day per excavator from 3873 to 4278 in March 23. It is total 10% of growth in productivity of HOE patches. Now come to the progressive PF up to February 23 versus progressive PF of October 22. Here you can see almost every project have a growth, and you can see some projects like Jayant. Jayant already achieved their benchmark PF. There is no question. And Krishila, we are working on it. What is the issue? Rest of all the projects have positive growth. This is the total NCL. Benchmark PF of NCL is 1.8, and PF of October were 1.78, which is less than benchmark, where when we were not using 9-meter drilling totally. When we have started using 9-meter drilling, November PF is 1.82. December, we have slide down 1.77. In PF January, we have 1.846, a growth, 1.845, a growth in February. Total growth is 3.65%. So this is the overall growth in total NCL in HOE patches PF. Now this is cost benefit analysis for every 1% growth. You have seen 3.65% growth in NCL HOE patches. So we have SME saving of 2,242 ton in annually, and now you can see in the same way DF saving, cord delay saving, and total financial saving of this adoption of 1% growth in PF is 1.69 crore rupees. Next. Come to the scope of improvement. As we can see, 3.65% growth. If we adopt this 9-meter drilling up to 100%, we can definitely achieve up to 11 to 12% growth. We have present 31 drill, and we are going up to 32% drilling. So we can achieve more in PF. Now come to the constant. It is my last slide. Here, no doubt, 6-meter is versatile, because if you have a preformed boulderage strata, you can go for 6-meter drilling blasting. Definitely, where watery holes, 6-meter is more preferable than 9-meter, because of the watery hole, where rate of drilling in 9-meter becomes less. And in upper layer of HOE patches, you definitely see, particularly in Dudhichua and Khadia, we had seen that heterogeneous strata are found, where 9-meter drilling results are very poor. With different types of rock formation, blasting results are definitely for 6-meter is better. So for decking, we can go with 9-meter with decking, but in HOE patches, there are large patches. Decking is not preferable, so we can go for a composition of 6-meter and 9-meter drilling in HOE patches. Thank you. That's all.
Thank you, Mr. Pandey. Good presentation for the HOE contractors.
Thank you, sir.
Thank you. We quickly move on to the third paper from Sassan Coalfields. It is mitigation of coal bench fire via introduction of pre-split control blasting. Sanjay Sengar, Abhilash Nanda, Ashish Kant, and Aditya Kumar Verma are the authors. Kindly introduce yourself.
Good evening, everyone. I am Ritesh Tiwari from Sassan Power Limited. Present over here for sharing our case study that how we mitigated a coal bench fire because of pre-split blasting. Sir, for the larger open cast mines having a stripping ratio 1:4, like SASAN, as we are dedicated for feeding our power plant with 55,000 ton per day to 60,000 ton per day. It is our utmost priority to have exposed coal seam that remains for 45 to 60 days. With this exposure, coal bench fire due to the spontaneous heating are our very major issue that we have to tackle day to day, which decreases our overall mine economics. So we developed this technique of pre-split blasting in coal for mitigating this fire issue in our coal benches. Next. So this is our diagram of coal method of winning of coal. As we have two coal benches, Turra as bottom bench and Pureva as top bench. At the time of mining, next. At the time of mining Pureva benches, when the coal seam remain exposed for more than its incubation period, it catches fire. At the time of dealing of it, as you can see in this first picture, one dedicated water sprinkler is deployed there, and with the help of backhoe, we are exposing that heated coal. It took full day to for firefighting, and in there is also a night view of that patch. Sir, as you all know, pre-split for SASAN is not a new concept, as we have already established a pre-split blasting in our dragline benches. Because of that, we are getting a smooth and competent high wall, and with least chopping time of dragline and optimized casting, we are able to win a Turra seam with high productivity. Next. So what made us to develop this technique? Sir, as our mine is spread over with a strike length of 4 kilometers, our whole mine operation goes into two zones. We call it north pit and south pit. When the coal winning goes on north pit, the south winning goes on development work like dragline cut progress, decapping, electrical layout, water management, and so on. So when we go to next pit at the time of coal winning, next, we see that our exposed coal seam caught fire, and which becomes very much difficult for us, and it is very difficult job to continue our production, uninterrupted production in Pureva seam, and which ultimately made us to lose our coal, which because we are not able to trace that fire, because initially when we are at the time of phase profiling, it is very, very difficult to dose that heated coal and heated fiery seam, and after the time of deploying diesel drill or electrical drill with the cable layout, and after the blasting, at the time of blasting with SME, DF, it becomes a totally unsafe working place for deploying our equipment and manpower in the risk. So ultimately this fire degrades our coal quality and makes unsafe working condition, and also decreases our machine productivity. So sir, this is the mechanism what we developed, and we have similarly replicated our dragline bench pre-split blasting with with pre-split blasting in coal with a lesser dia. Next. Sir, here we can see in the first picture all the holes after getting cut line, after a linear cut line of coal winning, we deploy a drill of 159 mm, or all the coordinates are plotted by the help of Minex and dedicated survey team with the help of DGPS. Then by seeing the parallelism because of IDM 30, with the help of IDM 30 Atlas Copco, all the drill holes are made in one line, and in second picture we can see how we have made on-site cartridges, SME cartridges for charging of hole. In this lower picture we can see holes are, both the adjacent holes are tied with the help of DF, and at the top of hole, all the holes are covered with SME, with N4 bag, with coal cuttings, and at last our result is all the holes are shorted instantaneously, and we have generated a crack, a linear crack. Next. So this was our development of pre-split charging, because it is a hit and trial of case of last 3 to 4 years, and we now last year we have established this technique. How we have improved improve our technique from 18 meter, 19 meter, and at last 20 meter. There all the parameters are written. In North Pureva coal with the depth of 16 to 18 meter, we have not received a good result in our high wall. And same then we did in mid Pureva coal with 18 to 90 meter, and we have taken the spacing of 2.75, and number of bags in each pre-split hole were 5, and we have got respectively good result than North Pureva. And at last at South Pureva, when we were dealing with South Pureva coal with the thickness of 19 to 20 meter, by keeping the spacing 3 to 3.5 and number of bag in each hole were 5, we have received and we have gained a good result. Even I can say it was an excellent result, and we have preserved that coal more than a year. It is still unfired coal seam, and we are taking that coal seam after 1 year. Next. This was the result at what I said in earlier slide. This was the result of North Pureva, that mid Pureva, and bottom of slide this is South Pureva. At this coal seam we are now winning our coal. You can see a particular half barrel in each of the slide, in each of the pictures. This results our even high wall with no roughness in the surface, which caused us to prevent from fire for a longer time. Next. And and in conclusion, I can say we have got higher productivity with stable high wall, and good confidence of working at the time of winning coal under a 20 meter high wall by winning with a combination of FEL and dumper. So from the SESSION, I can recommend this for all mining professionals to deal the fire with this technique. Thank you.
Okay, thank you for finishing within the time. Moving on to the second last presenter here, Mr. Navin Rai from NCL, good blasting, good fragmentation, fundamental problems. Navin.
Thank you, sir. Slides, please. I'm Navin Rai. I'm Chief Manager of Mining at CMC. But this presentation and article that I have submitted is more based on my experience as blasting manager in Khadia project. In this presentation, I am trying to focus on two things. First is drilling. Please be on first. First, I will be focusing on importance of drilling. Because drilling is the most neglected portion in blasting. Bearing dragline benches, where drilling takes a paramount importance, and the least important is in HOE patches, where you are blasting from more than 700 to 1,000 holes per day. Okay, next slide, yeah. So, before any process begins, surveying the location. Surveying the location means from where your blasting patch is going to happen. Rock types, when you are working on the topsoil, you are working on the Pureva exposure, you are working for Turra exposure, your hardness varies a lot. you plan your drilling patterns. I can tell you by my experience of 3 years, it rarely happens in outsourcing patches. Outsourcing patches are left to themselves. They simply keep on putting their holes on the decided pattern of, say, 4 by 6. But on the day of blasting, we don't know which is our burden, what is our burden, and where is our spacing is. Unless it's pre-decided that where our first hole is going to blast, then the second, then the third, then the fourth, not the holes, but the rows, where it's going to move. Because there is a basic empirical relation between B and S, that is burden and spacing. Burden is always less and spacing is always more. And if the process of your blasting gets changed, your fragmentation is badly affected. Next slide, please. This slide is just to show you a very practical experience as to how you will identify your blasting as good. The moment you say, after all these safety clearances to your short pattern blast, you can see the first row movement, first hole movement. If it moves, be sure that subsequent rows will move and you will get a good blasting. Fragmentation is always, you can see fragmentation complaints, you can always have. The moment shovel comes in and it starts to lift, your fragmentation aspect will be spoken of whether your blasting was good or bad. Shape of muck piles. Will be always an inverted V. You can tell that your whole blasting patch has moved. Depth of recovery. Depth of break means what amount of recovery you are getting. For me, anything above 90% is excellent. Means if I am drilling a 9-meter hole, 10 meter, your recovery should be 9 meters. And last is the fractures and the back break in the high wall. If your blasting material, if your last hole has moved away from it, be sure that you will be getting a proper recovery, you will be getting a proper fragmentation, and your everything will be okay. Please, next slide. So I am trying to focus on drilling, and in the second aspect I will be focusing on HOE and the cost saving and what cost saving is potentially possible. By drilling management, reduction in drilling cost. This is again quite small amount, so being a public sector we don't consider it much. But if any amount of over drilling will result in more consumption of explosive, lesser number of holes in a blast patch should be the main emphasis. Next slide, please. Just to highlight what the cost of blasting costs us nowadays, it's 14% of the total cost of the production. So any waste, any improper utilization, poor discipline will result in higher cost of production. Next slide, please. One more point that we regularly face, particularly in the HOE patches, is overloaded holes. What happens that since we are unable to monitor all those 7 to 100 holes to 1,000 holes that is being charged in a day, outsourcing persons have a tendency to get it charged in more than what you have told. Suppose if I have told that 52 kg of explosives has to be charged, they will have a tendency of charging it to 55 or 60 kgs, thinking on the thing that they will be getting a good fragmentation. But that is only a waste of SME. You get a poor fragmentation because energy escapes through the least resistance path, that is the stemming column. The moment you charge more, your stemming column gets reduced and energy escapes, and you are getting even a worse recovery and fragmentation than what you will get out of a undercharged hole. Next slide, please. Okay, on charging management, I have just tried to focus on the last two lines that more concerning is the potential negative impact to safety, fly rock and air overpressure. When we used to blast on the top benches of a Khadia project, we used to get complaint from IWSs. IWSs used to be quite far off place from our project. In between there are all sorts of workshops, national highways and railway projects. Then our IWSs comes into picture. That was just due to air over pressure. And fly rock, anybody who has done blasting must have an experience that some of the rocks have flown past through his guards, through his heads. So that is a very important safety aspect. Overcharging is not only from a cost point of view, but from safety point of view. Next slide, please. Downstream impacts from blasting activities are very difficult to quantify, but analysis of every blast can be done. Nowadays, with the deployment of 20 cubic meter shovels, if we are blasting like something like 50 meters of advanced blasting, you can see the difference of productivity, means you can measure in terms of meters that it has moved per day. If you have a good blasting, the advancement, the productivity of your shovel will increase quite dramatically. In Khadia project, we have seen it varied from 10,000 production per day to 15,000. If you had a good blasted material, your shovel could produce more than 15,000 cubic meters in a day. Now, as to cost cutting measures, I am just showing you how the variations in the normative PF of variable. I have taken just 5 major projects of NCL, which consumes most of the explosives. You can see Jayant is on the upper side of the norm, that is 2.18, but we have projects like Nigahi and Namlori, which are struggling at 1.55 to 1.57. Next, please. This is also of coal. Next, please. Shovel dumper also you can see that 1.32 to 1.84. This is the level of variation that you are getting in the same set of drilling and blasting pattern. Geology is obviously changing, but 1.32 and 1.84 I don't think is comparable. Next slide, please. Next, please. Now, in this part of my presentation, I am trying to focus as to how the cost saving can be done by achieving a PF of 2. Earlier presentation by Mr. Pandey had spelled out that achievement, the target set by CMD sir is of that of 2. But how we will achieve that, and by achieving it in theory, what is the cost that we are going to save? So these are just statistics. Here the second point is important, just the backslide. Matching excavating equipments by HOE contractors is a must. Means it should be able to lift in 2 batches. If you are drilling and blasting a 9-meter hole, so effectively we will be getting around 8.1 or 8.2 meters of blasted material. So in 2 lifts we should be able to lift. The logic behind this is that if you are currently now, okay, so I will be concluding. Next slide, please. Okay, larger blasting patches so that you are not blasting daily and you are able to set the patterns quite according to your requirement. Next slide. Now this is quite important. You have to fix the burden and spacing of the blast hole. Means length and the breadth of the patch is very important. Right now you will be seeing it's in circular or in arc form. They will be drilling anywhere depending upon the number of PCs or shovels that they are deploying. They have no length and breadth. Without length and breadth, you cannot design how you will open the first hole, first row, second row, third row, where the whole material will be moving. So this is quite important. Next slide, please. This is one point that I have practically found, that some holes are deeper, some holes are shorter. And if you are charging 800 holes per day, you are unable to monitor. This you will be having a complaint from both the sides. If you are achieving a poor PF, your contractors, your suppliers will be complaining, and your HOE will be talking about poor productivity on account of uneven faces that they get. So shorter holes, longer holes variation, it matters. Next, please. Here again, the fixing of normative PF based on past performance is not very scientific. Like right now, what we are doing in IOCL patches of LTA contracts, we are conducting few studies of pre and post level surveys. Now this is what we should be doing with our rate contract suppliers. Now one of the major problems that I faced was the availability of survey department for measuring pre and post levels. Here of course some new technologies are emerging, so drone surveying can help us in determining pre and post level surveys. Next slide please. It is about a wet hole. I think we should go to the next slide.
Please conclude, Naveen.
Sir. Okay, sir, this is for using of down the hole bottom initiation. Right now, there are constraints of limited magazine storage. This can always be done by increasing because or ever increasing production. Next slide, please. Okay, next slide, please. Now, this is just a pure calculation that if we achieve a PF of 2 in just HOE batches in just 5 projects of NCL, we can save up to 91 crores. Cost of accessories and cost of drilling has not been included in this study. So if we conclude if we are able to improve in our shovel benches, if we are able to calculate for all the accessories, I think it will be well more than 100 crores. Thank you, sir.
Thank you, Naveen. Our last presenter is from Samir, IIT Mumbai. They will be presenting the paper online. So by the time they connect, if anyone from the audience has any questions for the authors seated here. Any questions for the papers presented physically here?
Sir, please. Sir, when we are getting a smooth and stable high wall without any roughness, which prevents us from continuous rubbing of continuous interaction between the air and means oxygen and coal. So because of that competent and smooth high wall, we are getting no fire at our Pureva seam as well as at Turra seam.
Is technical team prepared for the presentation? I think we can go ahead with this IIT Bombay presentation, and after that, yeah, they are connected. So Jasprin, can you hear us?
Yes, the last paper for the session is geocoding of ground-based SAR images over a coal mine, being presented by Samir, IIT Mumbai, Jasprin James, Arun Kumar, Raymond Pinto, Supriya Bhinde, and Professor Y.S. Rao. You are welcome. If you are connected, you can begin your presentation.
Sir, can I proceed with presentation?
You are audible to us, so you can start your presentation.
Yes. So very good afternoon to one and all present here. So this is my presentation, geocoding of ground-based SAR images over a coal region. So actually we have to map it. That is our criteria. So I will just going through the statement. So basically, our images that are obtained, they are in 2D domain. 2D domain in the sense X and Y. When we actually map it into the 3D space, we need to convert it into a 3D domain. So this is the particular problem, converting the 2D image into a 3D plane for mapping it into the Google Earth. So for making this task, we can't do it directly. We need to give it some model or some other algorithm that will actually place the 2D domain image into the 3D domain. So our main objective is basically convert the entire data that is in 2D domain into the 3D domain and identify the GCP points. So identify the GCP points of strong reflectors such as CR and then place it in the particular position. So also we are doing 3 different angles, that is we are finding out the positions, that is 0 degree, -5 degree and -10 degree. So 3 different angles we are finding out and mapping it into the particular region. So why basically geocoding and why is it required? So firstly, we need to calculate the particular region and then map it into the particular parts. This is only possible if we have two different points, that is lat long point 1 and lat long point 2. So basically we are using 2 different points, that is one is a GBSAR point in which that lat long position of the GBSAR is considered and then the CR position is considered. So calculation of parameters is required. Secondly, accuracy. So accuracy, for considering the accuracy, so for considering the accuracy, we have 2 different points, selection of control points and the quality of positioning. So we are using 2 different things, that is the corner reflector
Jasmine, try to speak. I think we can hear you. You are audible, Jasmine. You can continue with your presentation.
Hello, sir, am I audible?
Yeah, Jasmine, you are audible. You can start with the presentation.
Okay. So this is my presentation. Is the slide visible? First slide. So basically, this is a presentation, geocoding of ground-based star images over the overburden dam. So basically, what is the problem is basically the images are in 2D domain, which I have to convert into the 3D domain. So this task can be achieved via some 2D to 3D conversion models. That is a transformation model, you can say. So to convert this, we need some models to be applied, which I'll be explaining in the upcoming slides. Then we have GCP points, strong reflectors, which is the GBSAR point and the point of the CR, that is the corner reflector. So 2 different points we will take and then we will map it. So we use 3 different angles also to particularly position into 3 different time. So what is basically geocoding? Geocoding is basically calculating parameters and mapping the 2D image into the 3D domain. So whatever you see, this is a GBSAR you can see here, which is placed and looking into a particular direction. Once you get the 2D image, if you have to place it into 3D domain, we need to consider two parameters, that is selection of control points and the quality of positioning. So mainly the strong reflectors are used, CRs are used for this positioning. And thirdly, these 5 factors we are supposed to consider. That is P. P is the position of the DEM or the DSM or R and the theta. Calculate the lines and the columns, that is place it in the center. We consider GBSR in the center position and apply the minimum Euclidean distance. After that, bearing angle conditions are done. That is 231 meter from the position of the GBSR. Then final mapping is done. So you can see the particular flow of the entire this thing, that is the raw echoes are collected. Then we need to check out whether we are correctly viewing the particular area, whether there is any movement of pixels or whether there is any disturbance. All these things we are doing, that is interferogram coherence, phase and wrapping, displacement map generation, and then geocoding. That is this process. In this process we consider two lat long position, that is the position of the GBSR and the position of the CR. After that, lines and columns are calculated. Then Euclidean distance. This is a range we are calculating and particularly placing in that particular region. So for 3 different look angle we are considering, that is 0 degree, -5 degree and -10 degree. So the DEM pixels are there. So you can see three different region, and we are also found out what area it is covering. Like 0 degree is covering the top dump and the middle dump and the lower dump. So 3 different regions it is covering, and I have also calculated total number of pixels that is calculating in this area, that is 1, 2 and 3. So we are particularly mapping -10 degree because it is giving a larger illumination of the particular dump. So you can see this is a DEM model which is having the 3D, that is the height information of the data. So height information of the data plus the actual 2D data gives you proper mapping in this particular region. So these are the results. Basically, it will include mapping of particular area in that, where here displacement map is particularly mapped. A displacement map, it is, so you can see the red region is actually the region where the displacement had occurred. And finally, we proceed with the mapping. So by concluding, I can say that we have mapped 0 degree, -5 degree and -10 degree, and results show clear mapping with all the angle positioning in that particular area in Google Earth. 0 degree shows the least number of points, that is the top portion. So we are proceeded with -10 degree, which is covering the lower area of the dump also, and -5 degree covers the middle area of the dump. So mapping of the coordinate points with exact DEM coordinates along with CR, as I said, we position one CR in particular position and then map. So two lat long positions give you the accurate mapping position. And finally, we mapped it as shown in the results. So this transformation model proves to be a good efficient mapping technique, which is shown in this slide. So this is how we have mapped. So it really gives good displacement mapping in that particular region just observed by the GBSR. That's
Okay, thank you. Thank you very much.
Thank you so much, sir. And with this, we have completed our presentation part. Now we will move to question and answer part. And we will try to make it quick. So please, if anybody has any questions, raise your hands. We will reach to you, and let's complete the session. So I think we have a question back there.
My questions to Professor S. Roy.
So, to begin, like the global scenario, as we have said, like the dragline is the cheapest way of moving the material. So if your geomining conditions allow, because you can't deploy dragline across all geomining conditions. If you have a larger, because as I said in the beginning, it's a high bench mining. So bench height is quite high because the construction of dragline is such. So wherever there is a possibility of deploying the dragline, people deploy because they get a huge cost advantage. Not only the single seam operations, but if you have a closely packed multi-seam operations, there also people have deployed draglines not to expose one coal seam, but also the multiple coal seam. And in those scenarios, they have practiced the multi-layer blasting, because that's one scenario which favors multi-layer blasting. Coming back to the India, because I was little surprised, then this 2496 size draglines was ordered, because this is almost obsolete. I don't think it's sold anymore, unless it's a specific requirement. So in global operations, the minimum size is 36 to 40 cubic meter bucket size dragline. So there's a scenario there. And as I said, just to reiterate, if geomining conditions allow you, no system can be as cheaper as the dragline for moving the material.
My question is, seeing the geometry conditions in the world and in India, what is the future of dragline mining?
It's a great, if your geomining conditions allow it, you should go for it.
What is the future of the present area? Whether there will be an increase in dragline mining or it will diminish?
Like in case of NCL, say for example, because NCL is a place where the geomining condition allows deployment of dragline of Thorasim. Here it should persist unless we deliberately, or because you see dragline mining requires a lot of planning. One of the reasons why NCL operations were mechanized and to the plan, one of the reasons was the presence of dragline. Shovel dumper system is a very flexible system. You can deploy any way you want to deploy it, whether as per the plan or not as per the plan, which is unlike the scenario in case of dragline. You have to follow the plan. If you fail to follow the plan, your mine will face a lot of bottlenecks. So if you are really planning driven, very systematic, I think there is no substitute to dragline. So if you meet those conditions, as far as future per se, if you are asking, future is great. Wherever geomining conditions allows the deployment of dragline, up to the multi-seam dragline operations, people worldwide are going for the dragline deployment. That's the scenario.
Thank you. If there is any other questions?
Any more questions? Sir, I have one question for Mr. Rai, sir. Sir, the case study of Sassan, which you showed, previously they were working in 2 sections. Now they have shifted into 3 sections. Do you think that in NCL, where in most of the mines where we work in tandem, all the draglines are in tandem, this cast blasting needs lot of dozering, and the vicinity of dozering or drilling continues within the dragline working range. Is it possible?
It's difficult to say as of now, but cast blasting, as I said in the beginning, is an integral part of dragline. Anywhere in the world where dragline is working in coal seam stratified deposits, both coal and the phosphate deposits. There are many phosphate deposits in Turkey, they deploy the dragline. So they deploy the cast blasting. In your case, since you are operating 2 draglines and that in the same level, your design will certainly not be the same as Sassan is doing, because they have a simple extended bench method where you will have the horizontal tandem. We may need to review, using the technology, what is the best way you can deploy the dragline. Is it the way that you are deploying, or there is a better way? Better way could be that we switch over, we tweak some of the dragline mining methods. May not be exactly the same vertical tandem that we used to practice like 15 years back in Dudichua, because I was in Dudichua 20 years back. So we were there, the vertical tandem may not be the same vertical tandem. but probably we can pick the designs. Globally, if I have to tell, there are over 20 dragline mining methods, depending on the requirements. The same dragline method, if you are deploying, say for example, in your case, for 1 kilometer strike, if it is a 400 meter, you have to review a dragline methods. Otherwise, your dragline will be doing too much of marching. Every 4 meter, it will be marching. So, idea is that when we simulate the entire operation, we minimize the unproductive deployment of dragline. Marching is one unproductive. As you said, we did a cast blast without thinking that what type of cast blast we require. A lot of dodging will happen. When dodging happens, dragline is idle. So instead of gaining because of the maximum cast, you might be losing in totality. So it's a tricky question, but it's worth exploring because the value that it might add is great.
Because for that very reason, they shifted their planning from 2 sections to 3 sections.
Are you still doing 3 sections? No, because when 2018-19, they were doing north and south section. That's what I checked.
No, they have shifted to 3 sections. 1 section is idle, 2 sections are working with dragline, and in 1 section they are carrying out drilling, blasting, dodging, making it ready for dragline operation. Okay, thank you.
Thank you so much, sir. With this, we have come to the conclusion of this session. Thank you all. And in this session, we have talked about one of the very key aspect of our operation, that is drilling and blasting, and also dragline software. And also, let me assure, sir, we are also implementing on a planning tool for dedicated to dragline planning under the digital transformation project. And you will see the better results in the coming years. So now, for the facilitation, I would request our rapporteur and chairman of the session to kindly facilitate the authors. First, I would request Ritesh Tiwari from Sashan Coalfields Limited. Sir. Before the facilitation, let's have the summary of this whole session from our rapporteur of the session.
सेकंड टेक्निकल सेशन में 5 पेपर्स प्रेजेंट किए गए, जिसमें डॉक्टर एस राय ने फील्ड स्टडी 20-30 ब्लास्ट की इन्होंने जो शासन पावर में की थी उसके आधार पे किया है, और इस बात पे एम्फेसिस डाला कि ओवरकास्टिंग किस तरह से ड्रैगलाइन की एफिशिएंसी को अफेक्ट कर सकता है, तो और साथ में ही बेंच पैरामीटर्स को भी ऑप्टिमाइज करके सिमुलेशन करके ड्रैगलाइन ऑपरेशंस को हाईली इफ़िशिएंट बनाया जा सकता है। मेन फोकस इसमें था। सेकंड पेपर जो ए.के. पांडे साहब ने प्रेजेंट किया वह मेनली HOE ब्लास्ट डिजाइन के ऊपर था कि हाउ 6 मीटर होल डेप्थ से 9 मीटर होल डेप्थ में चेंज ओवर करने पे ब्लास्टिंग इफ़िशिएंसी और ब्लास्ट परफॉर्मेंस पे PF में करीब 28% का NCL ने गेन किया, और फ्यूचर में इसमें और भी अधिक अगर हम काम करें, अभी जो 1% जो 9 मीटर ड्रिल लॉन्ग होल ड्रिल किए जा रहे हैं वो 100% पे अगर हम अचीव करें तो इसमें 10% और ग्रोथ होने की संभावना है। तीसरा पेपर रितेश तिवारी शासन पावर के द्वारा प्रेजेंट किया गया। इसमें प्री स्प्लिटिंग के द्वारा कैसे हम लेस इंक्यूबेशन पीरियड के जो सीम्स हैं जिसमें फायर के चांसेस हैं उसको कंट्रोल कर सकते हैं, और बेंच की स्टेबिलिटी के साथ साथ परसेंटेज ऑफ कोल रिकवरी को कैसे हम बढ़ा सकते हैं, इस पे एम्फेसिस दिया गया। और ये पेपर के द्वारा ये प्रेजेंट किया गया कि 60 डेज़ का जो इंक्यूबेशन पीरियड था वो बढ़कर करीब 1 साल हो गया, जिससे कि कोयले की जो रिकवरी के साथ साथ क्वालिटी भी इम्प्रूव हुई। काफ़ी इंफॉर्मेटिव पेपर था, क्योंकि हम लोग भी NCL में सिमिलर कंडीशंस में ऑपरेट करते हैं, तो ये पेपर हम लोगों के लिए भी काफ़ी इम्पॉर्टेंट है। चौथा पेपर नवीन राय साहब के द्वारा प्रेजेंट किया गया। इसमें इम्पोर्टेंस ऑफ एडवांस ड्रिलिंग मैनेजमेंट एक्सप्रेस किया गया। हम आफ्टर ब्लास्ट किस तरह से ब्लास्ट का परफॉर्मेंस जज कर सकते हैं, इसके ऊपर फोकस डाला गया, ताकि नेक्स्ट ब्लास्ट हम किस तरह से रीडिज़ाइन करें, इस पे भी एम्फेसिस दिया गया। ओवर ड्रिलिंग से किस तरह से हम अपनी इफ़िशियंसी हमारी होती है, लगभग ये 14% हम अपनी इफ़िशियंसी फर्दर बढ़ा सकते हैं। ब्लास्टिंग कास्ट जो कि टोटल कास्ट का 14% होता है, इससे काफ़ी हद तक रिड्यूस कर सकते हैं। इस चीज़ पे एम्फेसिस दिया गया। हमारा जो लास्ट पेपर था वो जियो कोडिंग ऑफ ग्राउंड बेस्ड SR इमेजेस पे था। सिंथेटिक ऑपरेशन राडार, इसमें प्लेन कोऑर्डिनेट्स को 3D लोकल कोऑर्डिनेट्स में कन्वर्ट करके हम लोकल इमेजेस जनरेट करके अपने डंप को, स्टेबिलिटी को देख सकते हैं। और काफ़ी सभी पेपर्स काफ़ी इन्फॉर्मेटिव थे और काफ़ी यूज़फुल थे। मैं सभी प्रेजेंटर थे उनका धन्यवाद देता हूँ।
Thank you very much, sir, for the concluding session. Now, I would like to request our chairman and rapporteur, sir. We will move ahead for the felicitation, where I would like to invite Ritesh Tiwari ji. Please come forward and receive the memento from our chairpersons. Now, I would like to invite Sri SS Rai sir. Kindly come forward. Shri A.K. Pandey sir, kindly come receive the memento. Naveen Rai sir,
After the facilitation of authors, I would request our Honorable Director Technical Operation, Dr. Anil Sinha sir, to kindly come and facilitate our rapporteur and chairman of the session. I know आज का दिन काफ़ी टायरिंग रहा है, बट तालियों की गूंज की आवाज़ आ ही नहीं रही है। काइंडली थोड़ी ज़ोर से ताली बजा दीजिए। Thank you so much, sir. And with this, we have come to conclusion of day one. And I have two important announcements to make. First, कल के जो सेशंस हैं वो सुबह 9 बजे से आप सभी इसी हॉल में इकट्ठा हो जाइएगा. We will be having our sessions on 9 AM onwards. And the second is कि आज शाम को आज की आपकी थकान को दूर करने के लिए we are having a cultural program from Brahma Kamal Institute of Dance. And it will be starting from 7 PM onwards. So all of you are requested to kindly attend it and enjoy the pleasurable full night. Thank you so much. Thank you for this day.